Hi, I'm Maida Shen. Today I will be discussing our paper Making Sense of Scientific Simulation Ensembles with Semantic Interaction. The motivation behind this work is helping scientists analyze and explore their data. Usually, scientists run simulation to understand a complex phenomenon that is expensive or even impossible to implement in real world. With a recent advancement of computational power, scientists are now able to run more complex simulations. They are also interested in understanding the behavior of a certain model or a certain phenomenon in different conditions. Therefore, a single simulation model as the one shown here wouldn't be enough to capture all the facts and features inside the data. Therefore, they run multiple simulations with different permutations of inputs, parameters, initial conditions, boundary conditions, or even computational models, producing what is known as an ensemble, a simulation ensemble. A simulation ensemble enables scientists to understand the model's behavior by studying the relationships and correlations between different ensemble members, determining parameter sensitivity and optimization. Therefore, the goal of our paper is designing a visualization tool that would be able to enable scientists understand and interpret the similarities and differences between and among ensemble members, understanding the influence and the sensitivity of input parameters on simulation's output, and finally determining the optimal parameter settings, studying the patterns and distributions in the data. Before we dive deeper into our visualization tool and visual approach, I need to go quickly over some definitions. So multiple dimension ensemble. We mean a simulation model that has multiple dimensions in terms of inputs and outputs. Semantic interaction. Semantic interaction is an approach in which analytical reasoning of users is inferred and in turn used to steer the underlying computational model. What do we mean by this? We mean that this semantic interaction is a user interaction technique which enables scientists to directly manipulate ensemble members or objects in a way that map interaction to models implicitly by captures scientists' insight and expertise, steering the underlying computational model. In much more details, what we mean by this is that the scientists will be able to directly manipulate and interact with different ensemble members without the need to understand the back-end computational model. Ensemble member. Ensemble member is a single simulation run. So for this paper, we have a couple of research questions. Our research questions are, can semantic interaction technique be adopted to explore simulation inputs and output parameters? Can semantic interaction be coupled with statistical displays to determine parameter sensitivity and optimization? What quantities are appropriate to include in the projection to give scientists the meaningful insights or the meaningful layouts that would lead to meaningful insights? Getting through the literature, we find that the majority of the work done in ensemble visualization focus either on parameter space exploration or ensemble space exploration. Few work have been done exploring both ensemble and parameter spaces. However, the majority of this work is not designed to handle high-dimensional ensembles. Therefore, this gets us into designing a visualization tool which would help scientists explore parameter and ensemble spaces, high-dimensional parameter and ensemble spaces simultaneously. This gets us into the idea of GLEE. GLEE is a graphically linked ensemble explorer. It's an exploratory multi-view visualization tool. GLEE is composed mainly of three views: an ensemble view for displaying simulation outputs, a parameter view for displaying simulation inputs and output parameters, and a statistical display for showing the distribution and the patterns inside the data statistically. Before I get into each of the different views in GLEE and the corresponding interaction, I need to go quickly over our visualization pipeline. Our visualization pipeline starts with the data source. In our case, would be the high-dimensional simulation inputs and output parameters. We take this high-dimensional inputs and output and we fit them into a similarity model, which projects this high-dimensional data from high-dimensional space to a low-dimensional space for visualization and interaction. Getting into the visualizations, each of the different views in GLEE has an interaction technique. With every interaction technique, we trigger the back-end similarity model, which call a machine learning algorithm which try to learn from user interaction and reprojects the data based on this interaction. Getting to the first view in our visualization tool, which is Ensemble View. Ensemble View is where high-dimensional inputs and outputs are projected from high-dimensional space to a low-dimensional space using weighted multi-dimensional scaling. Each member here represents an ensemble member. This ensemble view is not a scatter plot. It has no axes or units. It's just a relative similarity. So what we mean by this, we mean that ensemble members are sitting near each other, are similar in terms of their high-dimensional data versus ensemble members that are sitting far apart. This means that they are dissimilar. In the ensemble view, we support several interaction techniques, one of which is observation level interaction. Observation level interaction technique is an interaction technique which is based on the principles of semantic interaction. And the idea is that you directly manipulate ensemble members. So maybe from the initial projections, the scientist didn't find meaningful insights, or maybe he disagreed with the initial projection based on his expertise and intuition. So he began grouping, like dragging, directly manipulating ensemble members that he believes is similar, forming several clusterings, then updating the layout. Once he updates the layout, the back-end machine learning technique tried to learn based on this, like this clustering, how these different clustering are similar in terms of what attributes they are similar. So in this demo video, we're going to show what we mean by semantic interaction. So in this case, this is a particle data set. The scientist would like to understand the relationships between fermions and bosons. So he began forming two clusters for fermions and bosons, and he needs to understand, like, in terms of what attributes are similar. So based on the reprojection, he get to know that weak hypercharger spin is what controls this. So this means that the back-end machine learning technique learned that these weights is what determine this cluster, like what differentiates these clusters. So this is really important, and it helps the scientist understand the similarities and differences between different ensemble members. So whatever ensemble members he has, and if he's trying to explore or understand how they're similar or dissimilar, he began like clustering by directly manipulating them. And this is really important, especially when the scientist doesn't have a lot of information or like prior knowledge about the model. It's also important because you don't need to depend on external controls. And this is really important when the data has high dimensionality, in which the scientist doesn't have a complete understanding of the model and is still early analyzing and exploring the data. One other interaction technique we support in Ensemble View is like subsetting. So maybe the scientist starts with an overview, like GLEE starts with an overview for the whole ensemble, and maybe the scientist is only interested in a subset. So he began selecting these ensemble members, getting this, and began interacting with them. So Ensemble View is mainly designed to help scientists understand and interpret the relationship between different ensemble members. So since this is a multi-view visualization, it's linked. So any interaction in the ensemble view would be reflected in the parameter view and vice versa. We have in ensemble view, we have seen the different ensemble members projected from high dimension space to low dimension space. In a parameter view, we have all attributes or simulation attributes in terms of its inputs and outputs. And we have a horizontal slider where each input or output is represented with a single slider. And the value on the slider is not raw data, but weights on attributes. And the point of using weights is that maybe if we use the raw values, they will have different scales, so it's hard to interpret. But having weights, you're just marking the importance. When you use a slider by manipulating, by increasing or decreasing its value, you're announcing the importance of this attribute. So initially, when we did an initial projection, all ensemble members have the same weight. When the scientists began interacting using an observation level interaction, the machine learning algorithm tried to learn the set of weights would differentiate these different clusters, and this is reflected on the parameter view. However, we also support another interaction technique in the parameter view, which we call parametric level interaction. And a parametric level interaction is mainly used to determine the parameter sensitivity. So if you're interested in exploring the influence of a certain input parameter on the simulation output, so you directly manipulate this ensemble, this attribute, marking its importance. So if we get here, in this case of this particle data set, the scientist was interested in understanding the influence of mass on this ensemble. So what he did is he get into the mass attribute and he directly manipulated by increasing its value, marking its importance. We get all ensemble members clustered by mass. But still, we can't know which one has a high mass and which one has a low mass, because as we said, ensemble view is not a scatter plot. It has no axes, it has no units. It's just relative similarity. So I can see that these clusters are similar, these clusters are similar, and this is maybe an outlier, but I can't determine which one of them has the high mass and which one has the low mass. So this gets us into the idea of having a statistical view. So far we have been using parameter view and its interaction technique, ensemble view and its interaction technique to get the similarities and difference between ensemble members and determining the parameter sensitivity. However, we still need to get the optimal parameter settings. And as we said, if you're inside the ensemble view, we have different clustering based on mass, but we didn't know which one has high mass and low mass because there are no units and axes in ensemble view. It's just similar relative distances. So we need to interpret this. We need to get the optimal parameter settings. We need to understand the distribution, and like maybe the scientist would be interested first in filtering or like subsetting ensemble members that have a certain pattern. Maybe he observes something interesting more in the statistical view that he needs to explore. So statistical view displays the raw data of the simulation, and it helps in confirming and verifying the conclusions we get from parameter and ensemble views. So in our case here, we use a parametric level interaction to get the mass, like get clusters the different ensemble members based on mass attribute. And we use the barrel coordinates to get to know which one has high mass and which one get to have low mass. So this is one point. The statistical view supports different statistical displays. We have 1D statistical displays through a box plot, a 2D display using a scatter plot, and ND using a parallel coordinate. So we're serving different types of statistics for 1D, 2D, and ND parameters. In addition to this, we also have like selection. And when we're speaking about selection, we have two modes of selection. Either the scientist selects certain ensemble members and hit subset, so it will pull down this, or like he maybe use a lasso selection, where he selects ensemble members that is interesting for him. So from statistical view, the scientists get to know that quarks has the highest mass and bosons has the lowest mass and fermions has like intermediate mass. So he's interested in these high weights of fermions. So he just have a lasso selection on this to pull out these ensemble members. Another view which we have is a cinema slider. So the point of having a cinema slider is that when you're working with 3D, when you're working with scientific data sets, you'll be working with 2D and 3D data. When working with 3D data sets, since we're not displaying a 3D object, we're just displaying a thumbnail of the different ensemble members, using the cinema view gives you the option of viewing data from different angles. So like as if we're doing real-time rendering, you're seeing your data from a different angle. Another case in which we can get is in situ visualization. When you're using in situ visualization, you don't have access to all your simulation outputs. You just have your inputs and metadata and some images. So this is a way of like viewing your data from different angles. And the advantage of doing this, like when you're viewing the data from different angles, is that it gives the scientist a way of seeing the data from different perspectives. So the clustering and the grouping of data will be different based on the view. So here we use the different cinema sliders to see the data from different angles. And each angle carry a meaning, and each angle carry a way in which the scientist can interpret to have a different grouping of ensemble members. So far, we have gone through the different views in GLEE and their corresponding interactions. Now it's time to go through a real-world example. We evaluated our data using some domain experts in the field of geosciences. They provide us with a simulation ensemble which constitutes of 50 ensemble members that models the effect of geological CO2 saturation at a site located in Richland, Washington. Each ensemble member here shows the CO2 bloom at a 1% saturation colored by temperature. From this initial projection, the scientist observed several interesting temperature patterns. So what he did is he grouped ensemble. He needed to understand what's the differences between these ensemble members. So he began dragging high temperature runs in one side, high temperature ensemble members on one side, and low temperature ensemble members on the other side. Then he updated the layout, performing an observation level interaction, what's common between these different ensemble members. So from this, he get to know that temperature and CO2 saturation is what differentiates these two clusters. This gets him into an insight that larger CO2 bloom seems to exhibit more variability in temperature. The scientists then postulated this phenomena is likely the result of interconnected high permeability pathways that lessen fluid pressure, which in turn affects the ability of CO2 to expand. Based on this, he needs to explore more how CO2 saturation affects this, how CO2 as a parameter influences this simulation ensemble. In this case, you need to understand the parameters like the sensitivity of CO2 saturation on the ensemble members. So he get into the parameter view, performing a parametric level interaction by increasing the weights of the CO2 saturation. Based on this interaction, he get to know that smaller CO2 blooms appear to be more circular than larger blooms. This observation guided the scientists to an insight that permeability correlation structure of the geological formulation exerts more control on bloom geometry. When the CO2 reaches longer radical distances from the projection map. He also, in this case, uses the statistical view, so he can use a statistical view, so he can get where high CO2 saturations are and low CO2 saturation. Based on this, he was interested in understanding the relationship. Based on this, he was interested in understanding the relationship between temperature and CO2 saturation. So what he did is he reset the pipeline, getting an new initial projection of the data in which all the weights are set to the same weight. And he began grouping ensemble members based on temperature, CO2 saturation bloom size, and CO2 saturation bloom shape. So he began clustering based on these 3 parameters, and he was trying to understand how temperature affects this. And he used a statistical view. If he observed like something interesting, he was trying to find something interesting from the statistical view. So he began grouping ensemble members based on temperature, CO2 bloom size, CO2 bloom shape. Then he performs an observation level interaction. From this reprojection, he get to know that permeability has a dominant relationship, which was a new discovery for him. Scientists didn't know beforehand that permeability would have an effect if he was like clustering and grouping temperature and CO2 saturation. Then he performed a parametric level interaction by increasing the CO2 saturation and see if there is a correlation between permeability and CO2 saturation. Then at this point of time, he needs to understand this relation more, and he wants to explain it more. So what he did is he used a cinema slider. So he's tried to see the data from different angles. So maybe he, based on this relationship or correlation, he could observe something interesting. From the scientist evaluation to our tool, we get into some conclusions and feedback from the scientist. He offers different perspective for analyzing simulation ensembles, inputs and outputs. Usually when the scientist analyzes ensemble data, he gets a summary statistics of attributes across all ensemble members. When you're doing summary statistics, you're losing some information. However, with GLEE, you're able to analyze input parameters, output parameters, finding the similarities between different ensemble members, determining the parameter sensitivity. So you're doing this in one big visualization tool, like you're doing it on one screen. They don't need to alternate and shift between different scripts or like different visualization tools. One other point is that the statistical view helps them in exploring the uncertainty and showing the distributions in the data. One other point is confirming the conclusion that they were able to derive from statistical and from parameter and ensemble views. In addition to this, they say like using cinema slider with 3 data set offers a different way for exploring data as they're seeing the data from different angles and from different perspectives. This helps them have different way in which they group their ensemble members, and this gets them to get more insights and more intuition. And when using GLEE is an exploration tool at the end. So they're trying to explore the data. They say that the performance was reasonable. So the time between them doing the interaction and getting a projection was like a couple of seconds. So it was really reasonable. However, GLEE has some limitations. One big limitation of GLEE is scalability. GLEE works well with at most 100 ensemble members. Going over 100 ensemble members can get into visual cluttering. However, this problem can be partially solved by having GLEE on larger displays. Getting GLEE onto larger displays will help us accommodate and get more ensemble members. We believe like usually a simulation ensemble size, a regular or a normal simulation ensemble size wouldn't be more than 100 ensemble members. One other problem is that the current pipeline of GLEE is dependent on derived data set or derived values. We don't handle spatial data sets, we don't handle time series data sets, or we don't handle ensemble or like image-based simulation. Maybe in future work, this is what we're currently implemented. We have papers on like spatial GLEE and image-based GLEE. So, but this version of GLEE is only working with derived statistics or the derived values of the data set. Our conclusion for this paper is that GLEE is an interactive exploration tool which helps scientists analyze and explore high-dimensional input and output parameters. GLEE fits human expertise and intuition into the computational pipeline by using observation level interaction, which is semantic, based on the principles of semantic interaction, for enabling scientists to directly manipulate ensemble members, so they're getting insights out of the data. So the different views offer different levels of detail. So the scientist can start with an overview first, then he like select some interesting runs, getting into more details. Or like if he from the beginning know which ensemble members he's interested in exploring. He just can't filter this out. So we start from an overview first to the detail, so we can alternate between the two different modes of interaction. Any questions?